Hello, my name is Dr. Jonathan Butsky. I'm not a medical doctor. Instead, I'm the robot doctor. If you had a robot and you told the robot its location, where it needed to go, and the path it should follow, would you be all set? In most cases, no. Even if a robot has all that information, it still faces the problem of how to make sure it gets there. This can be a particularly challenging problem if the path it is supposed to follow goes close to obstacles or near dangerous machinery. The robot must be very careful to follow the path exactly, and even then, problems can arise. What if the robot drives over a rock, gets bumped, or a strong wind starts blowing? These real-world issues can cause the robot to drift off its desired course through no fault of its own. In Lesson 108, we will talk about controls, how the robot executes its plan and corrects for errors along the way. We'll be talking about vectors in this lesson, so be prepared to take notes as we learn how to follow a path. Following a path is an important part of a robot's movements. We almost always want the robot to move to a particular position or move at a precise speed, all while adjusting for any errors or disturbances it encounters. Let's look at a simple example of you riding a bicycle and look at one type of control we want to have: control over our direction. If you're trying to ride safely on the side of the road, you don't want to end up veering into a ditch or into traffic. There's a path you want to follow. As you ride along, potholes, sticks, and wind gusts all cause you to deviate from the path you want to be on. We call these outside influences disturbances. When you encounter a disturbance, you automatically correct by steering back toward the desired path. The robot needs to do the same thing with its controls. First, it must determine where it is and calculate errors in relation to its desired path. Then it needs to figure out which way to turn and how much to turn. Hey robot, can you follow the line? You want the robot to control the steering, but to do that, it must know what path it is supposed to be following.
In robotics, we usually call this path a trajectory, and it defines everything we need to know about the robot's desired positions and speeds. The trajectory consists of a sequence of points, commonly called waypoints. For ground robots, these points could be simple x-y coordinates giving the position, or they could be three-dimensional, having not only x and y, but they may also include an orientation angle. The trajectory might also have other information. For example, if we want the robot to travel at a specific speed, we will include a desired velocity at each waypoint. That tells the robot how fast it should be going and when to speed up or slow down.
The robot will have a planning function that creates the trajectory. The question we need to answer is, what does the robot do with it? How does it turn a trajectory into commands for the steering system? That is, how should the robot steer to get to the next waypoint on the trajectory? Let's think about what information we have to help solve this. We have a desired position from our trajectory. As an example, we'll assume that we want the robot to go up along the positive y-axis. We can also measure our current position using our sensors. For an example, we'll assume the robot is currently at a position of 2, 4. Maybe we just swerved around a rock. What do we need to do? Intuitively, we are to the right of our desired path, so we need to turn to the left to correct our position. One popular way of solving this is called proportional feedback control. Feedback means that it compares the desired value with the current value to find the error. It feeds back the current value to find a new value. It's called proportional control because the output signal is proportional to the size of the error. We can visualize this type of controller like this.
The robot has its desired input signal. That's the trajectory the robot is trying to follow. And it has the specific position along that trajectory where the robot is supposed to be. The robot also has its actual position where the robot really is. The controller uses these two positions to determine which direction to go and how much to turn the wheels. Now, as the robot continues to move forward, the position has changed, and that new position is fed back to the beginning of the controller to determine the next error. When the controller combines the actual and desired positions, it is calculating the error, how far away the robot actually is from the path. In our case, finding the error is easy. We can just look at our X position. But that doesn't work if we are going in the negative Y direction. In that case, we would be on the left of the desired trajectory.
We need a more robust method of determining which side of the line we are on and how far away it is. Let's first make a new way of representing our line by using its start and end points. Unlike normal lines, our trajectory has a direction to it. You follow the trajectory from start to the end. And since our trajectory is provided for us, we already know these 2 points. We'll write our line like this, using S to E as shorthand for start to end. We call this format the vector format for a line, and we'll use an arrow over the name to indicate that it is a vector. The vector is more than a single number. It is a column of numbers. Our vector has 2 elements. The top one is the difference in the x-coordinates between the start and end points. The bottom element is the difference in the y-coordinates. Now we can use an easy method of determining which side of our line we are on. Imagine our line has its start at the origin and its endpoint at 0, 10. Then our line vector would have the first element as the difference in the x-coordinates, and the second element would have the difference in the y-coordinates. Simplifying, we get 0 over 10. Now imagine the robot is at 2, 4, and let's make a line from the trajectory start to our robot and put that line in the same format, using S to R for start to robot. And we get 2 over 4. We can use what is called a cross product to determine which side we are on. The side will be the cross product between our trajectory line and the line going to our robot position. So how do we calculate the cross product? If we label the elements as A, B, C, D, we get the cross product by multiplying A and D, then subtracting the product of B and C. We multiply in the shape of an X, hence the name cross product. In our case, that would be 0 times 4 minus 10 times 2, giving us 0 minus 20, or negative 20. The number isn't important to us here, however. What we want is the sign of the answer. Since the answer is negative, we know we are on the right side of the line. If it were positive, we would be on the left side, and if we are on the line, it would be 0. Now that we know what side of the trajectory we are on, we still need to know how far from the line we are. We can use the vector form of a line to find this distance. We will use 2 new concepts to find this distance. First, the dot product allows us to multiply 2 vectors together to get a single number. The second is the normal to the trajectory. The normal is simply any other line that is perpendicular to our trajectory line. The distance is equal to the absolute value of the dot product between the line from the start point to the robot position and the normal to the trajectory divided by the magnitude of the normal. Let's break this down into smaller parts. The first thing we need to do is find a line between the start point and our current position. We can make this line using the same vector notation we used for our trajectory line. We take the difference in our x-coordinates for our first element, and the difference in the y coordinates for our second element. Using our example of moving in the positive y direction and substituting in our 2 points, we get 2 minus 0 for the top and 4 minus 0 for the bottom, giving us 2 over 4 for our line from the start to the robot. Now, the second thing we need is the normal, a line perpendicular to our original trajectory line. This is easy to generate with the vector. If you swap the top and bottom elements and negate one of the terms, it is always perpendicular to the original line. In our example, our normal is negative 10 over 0. We will also need the length or magnitude of the normal line. We can use the Pythagorean theorem to determine this. Using the x and y components of the vector for a and b, we get plus or minus 10 as our answer. Since length is positive, we can discard the minus 10 possible root and arrive at our final answer, 10. We use the double vertical bars to mean the length of a vector. Now we have everything we need to find the distance. Evaluating the numerator, we perform the dot product, multiplying 2 by negative 10 and adding the product of 4 and 0. We get the absolute value of negative 20 plus 0, which is 20. Divided by 10 gives us 2. So we have calculated that we are 2 meters from the line. And that's it. We now know which side of our trajectory we are on and at what distance. The final step of our controller is to translate the error signal into a steering angle. This is where the proportional part comes into play. We use a constant factor called the proportional gain to both scale and translate the error into the correct units. For example, our proportional gain might be 3 degrees per meter for our robot. Looking at our steering controller, we know our error is 2 meters, and we are on the right side of the line. In this case, multiplying our gain by our error, we would command the steering wheel to a position of 6 degrees, causing our robot to turn to the left and get closer to our line. Our robot can now successfully follow a line. We have looked at the elements that make up a proportional feedback controller and have examined how to use the vector notation for a line to find which side we are on using the cross product and how far away from the line we are using the dot product and the normal vector. With these tricks, the robot knows how far off and in which direction from the desired line it is. The robot also knows how to adjust the steering motor commands to get back on track. Now, for this week's challenge questions. Our robot wants to follow a diagonal line going through the origin and a point at 10, 10. Question 1. If the robot is at 2, 3, how far away from the line is the robot, and on which side? Question 2. If the proportional gain is 15 degrees per meter, what is the commanded steering angle from the controller? I'm John the Robot Doctor. See you next time.
You can find these lessons at wqed.org/therobotdoctor.
Hey robot, good job following the line. What are you doing now? I'm the Robot Doctor. Think I'll join you.